So we're going to get back to those. All right, so that's our goal for today. So starting with the average value theorem. All right, so here's what a typical problem would look like. All right, so a proficient level problem, so a very typical one. We have find the average value of a function over the given interval. That's going to be my part A. So that's going to be part A. Find the average value of the function over the given interval. And then for part B, we're then going to ask to find the value or values of C that satisfy the mean value theorem for integration. Okay? And if necessary, we're going to round to 2 decimal places. So, before I actually do this problem, I'm going to talk about the concept. What is the average value theorem? As we learned from the video last night. Okay? So basically, here's kind of what the visual was happening for this average value theorem. So we're saying, okay, we have some function. So let's make that function there. And I'm going from A to B. Okay? So I have this function that I'm going to go from A to B. And I already figured out from our last class, if I integrate from A to B, that is equal to the area under the curve, right?
Yes.
I hope y'all know that. So the integral from A to B, that is my area under the curve. So, and we know that area under the curve is equal to the integral from A to B of our function. You agree with that? That's what we've been doing. We've been finding area under the curve. That's what integration is. That's our main thing. That's the main answering the question of integration. Okay, so the mean value theorem says, okay, that's a funky shape that's hard to deal with. Okay, so it's a weird taking shape. So they said, okay, what is there? Is there some place on here that I can make a perfect rectangle that happens to have the same width as my interval, but when I make the rectangle, it has the absolutely same area as the area under the curve. And then, so we're trying to figure out where this rectangle would be, and assume my drawing is good, such that this area here of the rectangle equals the area under the curve. That's what the mean value theorem of integrals finds. We want to find the area, we want to find this rectangle. And how do you find area of a rectangle? Base times height, right? And so our base is this distance. And so that's going to be B minus A is our base. And our height is going to be some y value here. We're going to call that f of c, because that's going to be the c value that we need to find. So it's our y value, because height is y. So whatever height I go up on that y-axis there to make that perfect rectangle, that's going to be the area of the rectangle. And we want to set this up so that the area of the curve is equal to the area of the rectangle. So our mean value theorem says integral from A to B of our function must equal the area of that rectangle. Okay?
So the base is always going to be equal to the interval?
Yes, because we're going to make that rectangle over the same width of the interval of the integration, okay. The area of the integration. So it's always going to be that same width there, is what we're making it up. Now, this is a perfectly legit formula, but we usually don't see it written like this because usually they're asking for that y value. And so we're going to solve this equation for f of c. So to get f of c, I just divide each side by b minus a. And so they tend to, instead of writing this integral over b minus a, you'll see it often written like this. And so this is our mean value theorem for integrals formula. also called the average value theorem. So if they ask you what is the average value of the function, that's f of c. I want to figure out f of c.
Okay.
That's our average value. So that's the average of where I would put that line so I can make a rectangle that has the same area as the area under the curve. That's all that means. So that's visually what's happening. You can think about it. And there's algebraically what's happening, the equation. Okay. Anybody still need that, or can I go ahead and erase? Everybody good? Okay. I need more room again. All right, so we figured out our formula, we figured out what's going on to this situation. And so now we're going to actually apply it to a problem. Okay, so looking at this problem, we want to find the average value of the function over the given interval. So right there, I see I want to find the average value of the function. I know I want to find f of c, and f of c is found by taking 1 over b minus a, the integral from a to b of f of x dx. Okay. Also, have your calculators out. I'm going to teach you how to do integrals on your calculators today. Okay. Yeah, some already know, but some don't. Okay. And so now I'm going to plug in what I want. So remember, this is my a, this is my b. So f of c is going to equal to 1 over 0 minus a negative 4. Integral from negative 4 to 0 of negative x squared minus 2x plus 5 dx. So just cleaning that up a little bit. Looks like that. Okay, so everybody okay with this? Question? I'll shake of the head. So that's just using that formula that I rewrote. Area of under the curve is equal to the area of the rectangle is solving for the height of the rectangle. So that's what we want to figure out. The average value is the height of the rectangle. All right. So now we have that set up. I'm going to, in a moment, when I teach you how to type it into your calculator, this right here is what we're going to type into our calculator. So we're going to actually evaluate that integral in our calculator. But I am going to require you to do one more piece of work before you can do that. Okay?
So, do we have to calculate?
No, you don't have to. Okay?
Is there a situation in which we like would need to?
No, but it does make it easier and saves you a little bit of time. Now that you've proved that you can do the fundamental theorem of calculus part 1, where you can do the antiderivative of the top minus the antiderivative of the bottom, I'm just going to let you say some work. Speaking of the antiderivative, the one extra work I need to see is I need you to find the antiderivative. So I need to see that on your paper. So what is the antiderivative of negative x squared minus 2x plus 5? Okay, and remember, I don't have to worry about plus c because when I do the top of the upper limit, upper bound minus lower bounds, the c's cancel each other out. And so I'm going to evaluate this from negative 4 to 0. Okay, this is all the work that needs to be shown on your paper so far. So now we're going to go to our calculator. It wasn't open yet. No, let me open it. Okay. Okay, so go to your home screen, and we're going to evaluate integrals on our calculator. To evaluate integrals on your calculator, you go to the math key, and you'll see down here at number 9 for mine, finite integrals. So FN integral. So finite has a beginning and an end for integrals. So we have a upper bound and a lower bound. So once you have that highlighted, you push enter. And it should pop up like this unless you have the old operating system. Most of them are updated to this system. So, use the old one? Okay. So you're going to have to do it in parentheses. So you're just going to have to remember the order I type these in. You're going to type it in. So you're going to put in the lower bound, comma, upper bound, comma, equation, comma, x, comma.
So there already is no need to put another cell.
No, only put the parentheses at the very end. Okay. So if it looks like this, you're just going to fill it in as we have written on our paper. So my lower bound was -4. So I'm going to do -4. Cursor up to the box at the top. My upper bound was 0. So I'm going from -4 to 0. So I put in 0. And then my function is negative. Make sure you use the negative, not the minus button. X squared minus 2x plus 5. And then the calculator you must tell the calculator, okay, I'm integrating with respect to which variable. And so I'm integrating with respect to the x variable. So you have to plug in the x again, the x.
So you don't have to worry about something in the story.
Yeah, so nothing's going to be storing that. So that's the reason why you have to have that in there. So it doesn't do what you did your last stored of x is. And then enter. Okay, it did all the pretty math for me, but I need the exact answer for the next part B. So how do I get this back to the exact answer? Convert it to a fraction. So you go to math, fraction, enter, enter. So 44/3 is my answer that I will do here. Okay. Yes, you got to go to the doctor, yes. I'm thinking. It might be a fraction. Oh, there should be no cube.
Oh, you put in place, never mind.
Yeah, you put it in the original equation, not the antiderivative. So put it back into the original equation. Okay? And so now let me go back to our original. So notice I put in the highlighted one. I want to see that because you want to prove that you can still find the antiderivative, but you don't plug in the antiderivative, you plugged in the highlighted one. So that's what's very important that you do that, because a lot of people will go the other direction. So I figured out that my integral is, we'll have to worry about that later, okay? So we're worried about, so we have that, and we figured out, what was it, 44/3?
Yeah.
Okay. And so my antiderivative was 44/3. So see how much, that saves some time. So I'm not requiring you now to substitute in 0 everywhere, minus substituting in -1 everywhere, and solving that out. So that's the steps I'm letting you skip now.
Do you need
Yeah, -4 and 0. Okay, and so that gives me 11/3 is f of c. So that tells me the average value is 11/3, or what's that as a decimal? 3.67. So I think it said 2 decimal places. Okay. So when I type it in on your computer, you're going to type it in as 3.67, but I need this exact answer to do my part B, because you need your answer here to do part B, and you don't want to round and round again. That's a rounding error. So we want to go to exact, only round at the end of our answer. So that would be our average value. So if I was going to draw that rectangle that has the same area as my original function, I need to go up on my y-axis to the point 3.67. And that'll give me the same area. Okay, questions over that? Now, part B. So we just did part A, find the average value of the function over the given interval. Part B says, okay, now I want you to find the values of C that satisfy the mean value theorem for integration. So I know my height, my y is this 11/3. So C is my x value. So I want to go back to my original function and set my original function equal to the height I just found, which is 11/3. So original function equal to the height. Some textbooks, because technically it says C, so technically you're actually plugging in f of C. So some people will switch this. I don't care when you switch it to C, either now or later, but do switch it to C at the end at least. So that's what I'm doing. Original function equal to that. Now I'm going to solve this. This is kind of pretty easy to solve. You know, this easy trick that you have if you're dividing by a fraction to get rid of fractions. I can multiply everything by 3. Just makes it a little bit prettier to work with. Make it equal to 0 by adding the 11 to each side. And so we have this function we solve. Okay, it's not a pretty one to solve, so you do the quadratic formula.
You just do that in your head?
Well, I did this part in my head. I mean, I just did it as I worked. Okay, so opposite of b, plus or minus, b squared minus 4 times a times c over 2 times a. Okay, and then you can just plug that into your calculator. Or you can do your solving polynomials. Everybody know how to do that? Huh? Okay, yours can't do that? Okay. But if you can always use also solving polynomials, so that's all the work I need to see on this. So we just go straight to our answers. And this one I do not have memorized. I get negative 2.53 and 0.53 when I round to 2 decimal places. Now, next thing you check, I have those answers. But remember, we are dealing with this interval from -4 to 0. So you must check these results and only use the C that falls in that interval. So the C that you use must be in that interval from -4 to 0. So which one falls in that interval? So this one works. Because -2.5 is between -4 and 0. This one we throw out. Because 0.5 is greater than 0. So it's not in our interval that we're looking at. So to answer my question, find the value of C that satisfies the mean value theorem. That would be C is equal to -2.53. So I rounded here at the end. And that is how you do average value theorem for integration. Okay, do problems, the first 5 problems. Okay, so now we had a little bit of time to work on that. I know you might not have got all the way through it, but you should be at a pretty close spot. I want to talk about the fundamental theorem of calculus, the next part of the fundamental theorem of calculus. So we've already learned our first part of fundamental theorem of calculus, and that just said, our first part of FTC said, if I wanted to find the integral from A to B of f of x dx, that's equal to the antiderivative evaluated at A minus the antiderivative evaluated at B. So we've been using that over and over and over again. We just finished using that on those other problems. So that's our first part of fundamental theorem of calculus. So the one we're going to learn today is, the key with it is we're going to do a derivative in a integral. So we're going to find the integral, if you work inside out. So we're going to evaluate the integral, and then that answer we're going to differentiate. Okay, now question. When I evaluate the integral from with this -4, I'm going to plug in -4 in place of every x. I'm going to get some number. I don't even care what that number is. I'm going to get a number there. When you take the derivative of a number, what is that?
0.
0. So I don't care what this number is, as long as it's a number. It's just going to disappear. Because when I do the derivative, when I undo that and go into the derivative, it's going to become a, you're looking at a 0 there, so you don't have to worry about it. So the key thing we're looking for, we need to have the derivative and the integral together. So that's the first thing we're looking at for this setup. The next thing you have to look at is I'm going to look at my limits. And my lower limit here must be a number, a constant. So the lower bound must equal a number. So it has to be some sort of number. So that's for the setup. So we have to check and make sure this sets up correctly. The next thing we're going to check for is the upper bound must be a variable. No, it's a variable. This variable must be the same variable as the variable of your differentiation, not the integral. So it must be the same variable as the variable of differentiation. The upper bound must be a variable. Okay. And then technically, the function must be differentiable and continuous throughout. So if we can find the integral, then all the ones I'm going to give you are going to be differentiable and continuous. I'm not going to give you any ones that will be difficult that you can't do yet. So for the theorem, that's also a requirement for so that you know. When you get to upper level calculus, you might have to deal with that. All right. I love this theorem because basically, I don't care what these lower limits because they disappear. And so when I integrate this, I'm going to do my antiderivative, evaluate it from x to -4. So I'm just, and so the -4 just disappears. So when I take the derivative of that, it's just going to become 0. And then when I take the antiderivative, it gets us back to our original function. So my answer, this is what's so nice about this. My answer is I just copy down this function, substituting in place of every t what that upper limit is. So I just write x minus 1. Done. Answer. That's what I say. It's that easy. The derivative of the integral of from -4 to x of t minus 1 dt is x minus 1. Done. Okay. Now I do add a couple steps later, but not too many. Okay. I look at this one and I see, okay, does it meet my requirements? Is there something wrong?
The number isn't in the bottom.
So this one it doesn't meet the requirement because the number has to be my lower limit and the variable has to be my upper limit. So what property have we learned that allows us to switch those limits? Negate it. So I'm just going to do that. So negative derivative with respect to x of the integral. Now flip those integration, those limits of bounds. So I have to do that one little work there. And so now I got my negative coming out. And then I'm going to evaluate this just like I did earlier. So what would that be? Replace the w with x's. And then distribute your negative. Oh, minus. Done. No plus c's, because the c's cancel out when you take the integral. So this is another one where we don't have c's. So that's not so bad. I just got to do that. Too fast?
Yeah, a little bit.
I get excited on these. They're so quick and easy. Literally, when I was a student and I was in your place, I was thinking, I must be doing something wrong. There's no way it can be this simple. It is. I wasn't used to this being this easy in calculus at that point. I know, I remember, I struggled my first year in calculus. I remember the feeling. It was actually my first math class I ever actually struggled in.
Okay.
So it was interesting. All right. All right, so let's look at this one. Uh-oh, what's wrong?
There's a 3.
Oh, there's a 3. So look at my upper limit. It does have a variable.
Just move that to the front.
It does have a variable, but it's not x. It's something else. So when we do that, we're going to have to use the chain rule.
Oh my goodness.
Okay, but it's a limit. It's a smaller chain rule. Okay. Yeah, it's actually pretty easy. Okay, so we're going to do the same process again. I do have my number at the bottom. I got variable at the top. It's just not x, so I have to realize I'm going to have to apply the chain rule. So the first step is what we've been doing. Replace every t with 3x. So negative 3x cubed plus 11. This should be t squared.
That's what I was gonna ask.
Yep. And that's 11 3x squared minus 39 times 3x plus 44. Okay, so that's my step 1. So I just replace everything, every t with 3x. Now I got to deal with that chain rule. So I look at my upper limit and I find the derivative of that. So what's the derivative of 3x? 3 times by the derivative of the upper limit. So I'm just going to times all of that by 3. That's all you got to do for the chain rule in this one. Okay, so you just remember to multiply by the derivative of the upper limit. So this right here. Derivative of that upper bound. All right, so now I got to do some algebra. I've already done it, so I'm going to save myself a little math, little brain work here. All right, so this is negative 27x cubed plus 99x squared minus 117x plus 44. Still need to times it by the 3. So that's negative 81x cubed plus 297x squared minus 351x plus 132. So still not too bad work, but that was a little bit of extra work there. Huh? So I still had the number in my lower limit, a variable in the upper limit. So I replace every t with the upper limit variable, upper limit, and then I times by the extra step, timesing by the derivative of the upper bound.
Okay, so the variable that we're going to be replacing with x is always going to be the one that comes after d.
Yes.
Okay.
Yeah, whatever that is, yes. That's the variable that we'll be replacing. All right, one more type that you might see. What's wrong here?
It's squared. Oh no.
The bottom is not a number, the first variables. Okay, if they're first variables, we're going to have to use our property of integral that says we can split it up. And so we're going to split this up, and I'm going to say this is equal to the derivative with respect of x of the integral, and I'm going to keep the same lower limit. And then I'm going to choose a number, any number I want. Okay, any number you want. A lot of people choose 0 because it's easiest, but remember, the number doesn't matter because they disappear. So you can pick any number you want of the cosine of z dz plus integral. Now, whatever variable number I chose here, that's going to have to be my lower limit here because I'm using that property where these have to match up to my original upper limit, x squared. Oh, d dz, d dx of cosine z dz. Okay. So I just broke it up. And I just choose a random number that I'm putting that in between. Because it really doesn't matter what that number is, it disappears. Then I undo my integration, the derivative. And so now I treat this as two separate problems. So we're going to first look at this side. What's still wrong?
X.
I got the x in the bottom, so I got to get the x to the top and the number to the bottom. So how do I do that?
Negate.
Negate it. So that's going to become negative derivative with respect to x. The integral from 0 to x. Cosine z dz. Plus, and then this one is fine. It's already fitting my rules. I'm going to keep it like it is. All right, so negative. What is the what is the derivative with respect to x of the integral of 0 to x of cosine z dz? Cosine of x. Just cosine, replace that z with x. So, and we still got the negating outside, so negative cosine of x. All right, plus, hey, how about this one? What would it be? Cosine of x squared times by 2x. Because this is not x, so I have to use the chain rule and times it by the derivative of that. So don't forget that. So I got to times it by it. So just making this a little prettier, that's negative cosine of x plus 2x cosine of x squared. Now make sure you write it as cosine. The x is squared, not the trig function. So it's not cosine squared x, it's cosine x squared. And that's it. That's the hardest one you can see. Questions over this fundamental theorem of calculus. All right, now try, let's see, we're going through number 12, 6 through 12. Okay, so for this section, I just want to do a little reminder. It's been a little bit since we did some of these. In math class, our position notation for our position function, that's our S of t. That looks kind of messy. S of t is our abbreviation for the position function equation. Our velocity function is v of t. And our acceleration function is a of t. And we remember, if we took the rate of change of the position function, that was equal to our velocity. So velocity was equal to the derivative of the position function. And then if we took the rate of change of that our velocity is changing, that's what acceleration is. So acceleration was equal to the derivative of the velocity function. So these are just kind of steps. So this one steps down. The derivative of position gives us velocity. Derivative of velocity gives us acceleration. Now that we know integration, antiderivative, we can go the other direction. So that tells us that if I take the integral of my acceleration function, that will equal my velocity function. The antiderivative of acceleration gives us our velocity. Because we undo that derivative of velocity equals acceleration. We undo it. So that's the same thing. And then what we're going to focus on today is if I were given the integral of my velocity function, that's also equal to my position function. More exactly, if I do the integral from time 1 to time 2 of my velocity function, the antiderivative of velocity is position. So that'll give me my position at time 2 minus my position at time 1. Doing that fundamental theorem of calculus there. Okay. All right, so terminology that you may or may not know. Okay. So we're looking at, right now we're just looking at motion along a straight line. So I'm just going to do a straight line in front of the class. Let's say I'm pacing in front of the class. I start here. Time 1, at t equals 1, I am here. Okay, I go over, stop, have a question, answer a question, come back. Alex has a question, answer a question, come back over here. And then I go back and end up here at the end of time. Okay? How would I figure out my displacement? is my distance, my ending distance here, minus my beginning position here. You agree with that? My ending position minus my beginning position. So anytime you're asked to find your displacement and you're looking at, and I give you the velocity function, displacement is equal to the integral from time 1 to time 2 of my velocity function. Because that'll give me my, when I do the antiderivative of velocity, that gives me position at time 2 minus position at time 1. Ending position minus beginning position. So I have this little space here. Now, sometimes, in that case, because I ended up to the left of my beginning position, that is considered a negative. So if you get a negative displacement, that means your ending position was to the left of your beginning position. If you get a positive displacement, that means your ending position is to the right of your beginning position. So if I get an answer, let's say I work out something and I end up my displacement is, say, negative 4.2 feet. How I would translate that is I ended up 4.2 feet to the left of my beginning position. So I would punch in on the computer, I'm going to put in the 4.2, so I'm not going to put in the negative. I'm going to do the negative tells me my direction. So it's giving me my direction on which side of my original position am I on that I'm looking at. Now, so if displacement is negative, you end up to the left of your original position. So if displacement is positive, what does that mean?
To the right.
You got it. So displacement is positive. I will tell me that I am to the right of my original position. So that's something to know. Okay, so that's all we're going to do on displacement. So very basics.
So T1 and T2 are initial.
So type T1 is my initial time, T2 is my ending time. Time 1, time 2. Beginning time and ending time. All right, distance traveled. Okay, my distance traveled, I'm not looking at positive or negative. Oh wait, let me show you the graphic. So let's say this is my velocity graph. So I was doing my velocity graph, and I wanted to figure out what is displacement represented on this visual graph. Okay. Remember, the integral of velocity is looking at the area under the curve. So this is going to be, we'll make this my time 1. We'll make this my time 2. Okay. And so I'm looking at this area here, and this area here. And what you're going to do with that integral is how you're going to get some positive or negative. It's going to end up being that top area minus the bottom area because it's under the x-axis, so that area is negative. And then plus area 3. So that the placement will work with that kind of looking if you're looking graphically. And that's how you can sometimes get negative and sometimes you get positive, depending if you have more below or above the x-axis on your velocity function. So that's what it's looking like on graph. Now, total distance traveled, I started over here, I went here, but I'm still traveling distances, although I'm going back to here. So I kept going a lot of distance traveling. So when I do the total distance travel, I want to add up all these distances. I don't want to add and subtract. I don't want to count this negative. I want to make this negative positive. How do we make negative positive?
Absolutely.
Absolute value. So the formula for total distance or distance traveled is still the integral from time 1 to time 2, but this time instead of the velocity, I need to look at the absolute value of the distance traveled. So that means I need to take the integral of the velocity, the absolute value of the velocity function of dt. And so in graphical means that's going to end up being area 1 plus area 2 plus area 3. So it's going to make everything positive. So you should always get a positive result. Algebraically, we have to remember, anytime we had absolute values, I'm going to have to make a piecewise function. This is going to be the hardest part. And we got to figure out when to break this up in that interval. When am I positive in that interval? When am I negative? And so I need to negate those negative ones. We're going to do this in an example. So this is just the theory behind it. Let's look at the actual problems. Okay, so here's the problem we're going to do. The velocity function in meters per second is given by the particle moving along a line. I'm recording this so you can take the notes later. It's going to be online. I post all these online. Find the displacement and the distance traveled by the particle on the given time interval. So that's my A. I want to find the displacement. B, I want to find the distance traveled. Round the answer to 1 decimal place if necessary. So we're going to start with A, displacement. All right, so to find displacement, I remember my formula. That's the integral. This is time 1, this is time 2. So that's going to be 1 to 4. That's the interval which I'm looking at of my velocity function. Okay. Alrighty. So what is the antiderivative of t squared minus t minus 6? Minus 16. Evaluate it from 1 to 4. Then I'm going to punch that into my calculator. Again, making sure you're punching in this original part here into your calculator. And you're going to get -9/2 or -4.5 if I go to 1 decimal place. All right, so what is that telling me? The particle at the end, the particle is 4.5 meters to the left of its starting position. Okay, so that's 4.5 meters to the left of its starting position. That's it for A. Now B is a little bit harder. So I want to figure out the distance traveled. So I'm going to set that up almost the same. I got the interval from my beginning time to my ending time, so 1 to 4, of the absolute value of my velocity function. Okay, so I got to go over here and make my piecewise function. The absolute value of t squared minus t minus 6 is going to be this piecewise function. So to figure out where it breaks up, you take what's inside the absolute value, set it equal to 0, and solve this. Luckily, this is it factors nice and pretty. Okay, t minus 3 and t plus 3. So I get t is equal to 3 or t is equal to -2. But I don't care about the entire interval. I only care about from 1 to 4. So only 3 is in that interval from 1 to 4. So I'm going to disregard that -2 because that's not in my interval. So now I'm going to make a sign chart at my beginning time and my ending time, and any of these numbers that come inside that in between my beginning and ending time. In this case, it's only the 3. Then I'm going to plug in some points. So let's say I'm going to plug in 2 into this and see if I get a positive or a negative. Because again, I just care about it when it's negative. So if I plug in 2, that gives me a -1 times a +4, which is negative. If I plug in 3.5, that gives me a positive and a positive, so that's positive. So it tells me I need to fix this interval here from 1 to 3. So I'm going to put here from 1 to 3, I need to negate my function. So I need to do the opposite of what's in the absolute value. So it's going to be -t squared plus t plus 6. The opposite of what's in that function. Now, when it is from 3 to 4, I get positive, and that's what I wanted. I want it positive, so that area is just fine. So I'm going to go back to my original function. And I'm going to use that from 3 to 4. You can include the 3 on the bottom or the top, just pick one, it doesn't matter which one, but it only include the 3 in one of those. So that's my piecewise function. So when I set this up, I have to break up this interval here into these 2 pieces I just developed. This is how you solve any absolute value integration. So this is going to be my top piece, which was from 1 to 3 of my negated equation. So that's going to be negative t squared plus t plus 6 dt. Then I'm going to add the area of the bottom equation. And in that bottom equation, we went from 3 to 4, because that's when it was positive, of my original function, t squared minus t minus 6 dt. Piecewise. Okay. So we have to break it up. So anytime you evaluate absolute value intervals, you have to separate them. Just like when we find the derivative of absolute values, we had to separate them piecewise. We got to do the same thing here.
So we have to include the intervals, like not intervals, but like x values?
Yes. So where this piecewise breaks up is where we're going to break up our integration. But we do have to make sure that this, where we ended here, is where we begin here. So it equals the original. Okay? And so now just do my antiderivative. So that's negative t cubed over 3 plus t squared over 2 plus 6t, evaluated from 1 to 3. And this is t cubed over 3 minus t squared over 2 minus 6t, evaluated from 3 to 4. I did this in my calculator. You can go back and check me. And I got 22 over 6 plus 17 over 6 for a nice, pretty final answer of 61 over 6.
What about that as 40?
Okay. Oh, this is 3, not 6. That's 3. Try why that's 3. Okay. 61 over 6, which is approximately 10.17 meters, or 10.2 meters. I guess I did say 1 decimal place. So what that tells me, although at the end, I was only 4.5 meters to the left of where I started, that object had actually traveled a total of 10.2 meters in that time frame. Okay, so that's what that's telling me. So the total distance that object traveled was 10.2 meters. Yeah. Sorry, I had to rush it at the end there. I'm ready to try to get through it. Is that far enough?
Well, just after to where the number last one, so it's fine.
Right there? All right. Whew. Okay. So since we didn't have time to finish, I'm not going to make you do the video so that you don't have any video tonight. Just make sure that you complete this assignment before Wednesday evening, at the end of Wednesday night. Okay? And then Thursday, we will talk about what we're doing on Thursday. Okay? Oh, let me pause this, stop this.